Good morning, ladies and gentlemen. Nice to feel your presence. So, what do we have today? There is a course of quantum transport. There are homework packages. And today I will talk about the second homework package problem set number 2. Since we are not many, let's just do questions in the usual way, right? If you have a question, just speak up. In this case, we have a more interactive presentation. All right, let me go through the problems and solutions step by step. As with almost any homework for any course, homework problems are separated on things which kind of you can run with, or another alternative is just to put some material which we don't have time to discuss in the course, or whatever it doesn't seem necessary to discuss such details. So sometimes it's been given as exercise. And the first problem of the set is surely an example of this. Transmission distribution from current. I wonder if you see what is on my screen, if you can read what is on my screen. Alternatively, I could zoom in, but yeah, sometimes it crashes with my Zoom, so I would be satisfied with any answer.
Yeah, I can read it. It's okay.
Fine. Right. And we have discussed quantum circuit theory, which we use in order to evaluate transmission distribution of compound circuits. Here it is. Transmission distribution tells you how many transport channels in average have transmission in an interval of certain transmission coefficients. So this is number of channels in an interval of transmission coefficients. Fine. And when we built up circuit theory, we compute currents. These currents are not electric, they're completely auxiliary, just for exercise with the theory. And these currents depend on a parameter which is called phi phase. Right. And for any transmission distribution, we can determine the current as a function of phase for any given conductor. Then, for instance, we combine these conductors and we compute I phi characteristics of the whole circuit. That's good. But what we usually want is transmission distribution. So it is, well, necessary or whatever handy if there is some way to revert this formula and to obtain transmission distribution from current phase characteristics. Good. That doesn't seem to be obvious task, but in fact, it is an exercise on a theory of complex functions, although it doesn't immediately look like this. And applying this theory, we arrive at inverted formula. Right. Kind of price to pay is that we have to take I phi characteristics at a complex segment. And yeah, one has to be a little bit careful from which side you approach this complex segment. All right. So the exercise actually is to understand for you how one can imply a power of theory of complex functions to this problem. It goes by steps, which kind of are intended to help you to make your life easier. First of all, it's some variable change. Second is applying Cauchy formula. And finally, some polishing, some convenient rewriting of this formula. All right, so this is formulation. The problem, again, it is what one can learn from this, that many mathematical problems can be successfully solved with a theory of complex functions, even those which do not immediately kind of call for this. Yeah, if you look at this formula, you don't see any complex numbers, so you are a bit in a confusion. Good. So let me now go through the solution. I have to switch to another set of documents. Here we are. Good. So first set. Eventually, all these Cauchy formulas come from denominator. It's operation with a denominator. And we just want to have a denominator in a little bit easier form. Right, and that can be achieved just by variable change. So we consider a variable, which is like this, and substitute it here. So what we have to do, we have to express sine square phi, which is 1 over z, and we have to express sine phi. Yeah, but what is sine phi? Some boring trigonometry. This is 2 times sine phi over 2 times cosine phi over 2. Right, and that becomes, let's see, z is 1 over sine squared, so it's 1 over z, and that is square root of minus of 1 minus sine squared. So that will be like this, cosine. Okay, we combine it and we arrive at this expression. Good. Then we have in variables z, we have a nice pole. We have a nice pole, right? So the problems arise if z is closer to real value at the interval of from 0 to 1. Right, if I could, for instance, draw a complex z, and right, that would be imaginary axis, and that would be real axis. And here we have this interval that goes from 0 to 1. Good. For any z which is not at this interval, the integral has no problems. We never touch 0. In the denominator. But yeah, if it's not, sometimes not the case. And if that is at this interval, one has to be cautious, and one has to think what is a small imaginary part of z, which is called epsilon here. Let me put a couple of z. So this is a little bit higher with a positive imaginary part, and this is a bit lower with negative imaginary part. And eventually, these values are not the same. They experience a jump if one changes the sign of this epsilon. Here, how to see that? Well, one can implement Cauchy formula. Right. And one can reduce this integral to principal value integral plus an addition. which eventually depends whether here or here. The sign here would change if epsilon is positive. All right. Then with Cauchy formula, we can express this integral like this. And we see that this part becomes real part of this expression apart from a factor. So we write it like this. Implementation of Cauchy formula. All right. Now we just want to reverse this variable. So we have z equals let's see, z equals t. So that means that sine we need to solve this equation to understand at which phase rather than z we have this peculiarity. All right, so we do it here. So now we the argument here is the phase, and right, it is a solution of this equation. Fine. I don't see what else I can add to this problem. Any questions, comments? Again, of course, you would not get it during examination, just to understand how mathematical part works in this course. Right. If you feel yourself kind of less confident with theory of complex functions, then please kind of turn a little bit back and look at it. It's not about quantum transport. Complex functions, it's really very powerful tool set for many mathematical problems. Good. Right. If there are no reactions, let me go to the next problem. Let's see. Yeah. I don't understand. Okay, it just written a bit different. I thought there was a figure in this problem, but anyway, let's make a figure. Eventually, one has to look here. And we compute transmission distribution for a particular system, for a particular nanostructure. And it is made out of quantum point contact, where all transmission eigenvalues are wrong. And next to it, we have diffusive conductor. So there is a circuit representation. In real life, it can be something like that. We kind of make a constriction in to the gas. So heat's depleted, and when it is white, it can transmit. So thereby we have formed a constriction with certain number of open channels, but in fact we have extra unintended problem. We have impurities nearby. And when electron traverses, it will also diffuse upon scattering on these impurities. Right. We want to solve this problem in a certain approximation. Conductance of diffusive part is much bigger than conductance of the quantum point contact. It means that this scattering at impurities disturb the transport only slightly. Yeah? Conductance is large. So in principle, if conductance is sufficiently large, I could just replace this connector with a shortcut and forget about it. All right, so we want to do this in a certain approximation. Let us see which steps we are supposed to do. All right, this is whatever one could evaluate it with these formulas, or one could just take it from the lecture. What we need are I-phi characteristics for each connector, for diffusive one and for ballistic one. Then one would introduce the notations. Let us see, we need to distribute phase drops and give the names. And I guess here I could put phase to 0. It's like a grounding, so any part of electric circuit can be grounded. The same here with phases. So this is 0 and drop over diffusive conductor, etc. And what we found here is phi. Overall phase. Good. Then there is a piece which one can regard as a physical reasoning. That's why it's yeah hard to formulate mathematically. One has to understand that the problem actually makes sense only at phases which are closer to pi. First, understand this, and then just go to the vicinity of pi and make approximations related to the fact that the deviation from pi is small. Fine. After that, we are able to solve this problem analytically, and we can put the solution into the formula and compute the distribution of eigenvalues. Right, most approximations are made explicit, and the last point of this problem is to compute certain characteristics of this distribution, namely Fanon factor. Well, there's explicit integral representation for this quantity. Good. So again, there's a formulation, and now it's something more practical. It's small exercise in a quantum circuit theory, of transmission distribution, and we're gonna make it point by point. So let me switch to the solution. Solution. Right, first point one. These formulas I find can be derived for each connector by using big formula and it's also explained it in the lecture how to do this. All right. Then we want to make a circuit out of it. Let me write it out here. Ballistic, diffusive. There are conductances. And there are phases. Yeah. Set. So let us, yeah, I can write this equation as it says. If you write it explicitly, it would be rather complex transcendent equation. Oh, just a sec. Yeah, in principle, no, sorry, it is. I did not put the drops properly. The drop here is phi minus theta. And that is GD. And here's a drop is theta. So one can one needs to solve for theta from this equation and then express current in terms of phi. It is a little bit complex. So we want to do the simplifications, approximation, and the relevant approximation is that GD is very big. It is very big, and what does this mean? Let's think of, let's use analogy with voltages. It would imply that the theta is almost zero. Now in electricity is, understanding electricity, it's important concept. So at this point, I would like to ask whether you kind of have a feeling for that. And if it's not the case, we need to work on this. Good. Let us look at this circuit as electric circuit. All right. So there are two resistors in series. Yeah. And there is voltage phi applied. What will be voltage drops at these resistors? If resistor is small, the voltage drop at this resistor is big. All right. If no, sorry. If resistor is big, all voltage drop supposed to be at this resistor. And the smallest resistor can be regarded as a shortcut. Yeah. So one could shortcut it. And this is equivalent to theta setting to 0. Right? It's not about quantum transport, just about general experience with electric circuits. Is it better now? Yes, it is negligible. That's why theta must be very close to 0. Fine. But there is some point where it does not work. And the problem is that this current actually, although, yeah, it is big resistors, small conductance, current is supposed to be small. But as we see, it diverges if this parameter is close to pi. So in this case, we understand that if phi is closer to pi, we got a problem with this approximation. Oh, good. Let us put them. What can we do? Right. So what is we are here now? Let us concentrate on the region where phi is approximately pi, and let me just consider small delta. I minus delta will be. Let us now rewrite the currents, so I can approximate tangent at argument, which is about pi, 1 pi, but this. And then it becomes the same equation can be rewritten in a quite simple way. Which can be solved. No, so sorry, it's zeta. Yeah, zeta, of course. Which can be solved because this is a quadratic equation for theta. We solve it for theta and immediately get the current as a function of phi. Okay, here we do it. We solve for theta, quadratic equation. And we write the total current. And well, we can play a little bit with this expression. If delta is bigger, this parameter bigger than GB, GD, two terms cancel each other. Square root is cancelled with linear term, and the rest would be 1 over delta. It means that the current is dominated by this resistor. But if delta is small, if of the order of this small value, something is complicated. Good, so now we have a formula for the current, and we need to invert it to obtain the transmission distribution. Fine, so next page. Right, then again, as several small approximations come into play. If phases are closer to pi, it means that this t has to be close to 1 as well. And we'd better talk about deviation of t from 1, about small reflection coefficient. Good. We apply the general formula to what we get, and we see that contribution, which comes, which defines density of eigenvalues, comes from the square root. So the square root makes this function non-analytical, and that's why application of Cauchy formula leads to non-trivial result. All right, with this we can determine I need to plot it to understand what it is. Let me plot this. So it's transmission coefficient 1, or alternately R2 is to 0. And here transmission coefficient goes to 0. I kind of inverted the axis. And this distribution, if I look carefully, I see that it diverges at small r. Well, this divergence is integrable, so there's nothing wrong with this. It diverges a square root. Another peculiarity is that this approaches 0 and distribution ends at some particular value of r, which is, let's see, right, 4gb divided by gd. So that's small r. So it goes somehow like this. So that shows how original distribution, where all transmission coefficients were run, is spread a little bit. It's funny to see that the spread is finite, that it is restricted by this particular value. After all, one can just make this integration and come with a analytical formula for Fanock factor. In this case, one also has to take into account that values of reflection coefficient are smaller than 1. In this way, one can evaluate this integral. Fine. That was all about transmission distribution. Let us see how we are doing with time. Oh, that's fine. Let me talk perhaps a little bit about more practical matters about transport of single electrons, because we encounter master equation, and that can be relevant in exam, and that can be also relevant in all in many other subjects which are not related to quantum transport. So it is generally instructive. Let us see. Single electron transistor. Okay. There's a question from Isaac. Usually only relative phase matters, but in this question it seems to work only with a phase close to pi. What seems to work? The approximation which we made works only for the phase close to pi, and it is relevant over there. We could, in principle, solve this problem, for instance, numerically without any making such an approximation that would deprive us from simple formulas. But yeah, in any case, what matters is a total phase drop over the circuit. We kind of fix it by setting one of the terminals to 0. Does it answer your question, Isaac? Good. So let us talk about a single electron transistor, SET. To remind, a single electron transistor is basically an island which can contain integer number of electrons. And we organize the transport through this island by hopping electrons through tunnel junctions. For instance, this is for current which goes from the left to the right. Good. It is perhaps just again extension of the lecture. We just want to make explicit the formulas which has been flashed during the lecture. Okay, what is important for us? It is the expression for Coulomb energy of the system. This formula is very important. That's why, as it is usual, concentration of evil. There is a typo in this formula. Who can correct the formula? Recalling lecture material, for instance. So just thinking about what is the electrostatic energy. Mm-hmm. Interesting. Let us try to recall electrostatics. So there is a capacitor of capacitance C with a charge Q on its plates. What is energy? Again, it's not about quantum transport, it's about electrostatics. One half. Okay, Q times V, and what is V? Yeah, both answers are correct if we take into account that indeed the voltage drop at the capacitor is Q divided by C, and energy is Q squared divided by C. And we have defined Coulomb energy as E squared divided by 2C. Then, if one recalls this, one understands that there is a little true missed in this formula. Electrostatic energy has to be quadratic in charge. Fine. All right. Now let us go with the tasks. What are the tasks? First of all, it is the shape of the Coulomb blockade diamonds in the plane of, all right, anyway, here it's 0, here it's V, and we have a plane of bias voltage and gate voltage. So, as we done in the lecture, there is a periodic set of diamonds where single electron processes are forbidden by energy consideration. And here we have a certain number of charges. Right, so this is again, so how to do this point? One has to check all possible processes which can change charge. Compute energy differences related to these processes. Ensure that all these energy differences are positive, so these processes cannot go, at least at 0 temperature. Right. The next task is to give the region where electrons go one by one. I guess we looked at it as a lecture. It's just a region, a diamond, which is adjacent to two values of n, for instance, n plus 1, n plus 1. In here, it's both charges. Then, for this parameter regime, we are requested to write down master equation. Okay, it's already training on using and deriving master equations. Right, and then compute the rates, and finally write the formula for the current. Good. Let's go with this task. One needs to compute all possible energy differences, and there are 4 possible transfers from the right to the left. This is to the left, and this is to the right, and in opposite direction from the left and from the right. So this is for all these possible things for n equals 0, and these are all possible things for n equals 1. Well, we can now for any expression like this expression is linear in bias voltage and gate voltage. So what does it mean in a plane? In a plane, any condition of the sort is gives you a straight line. All right. It is one condition. There are 4 conditions. So if you look attentively, there are 2 parallel lines, and there are 2 lines in this direction. There are 2 parallel lines in a different direction. So that finally gives you a shape of a domain at certain value of n. N is the number of excess charges. Good. Is this kind of technique clear? I always thought it is, but it's been already a number of years ago. It was a student who did a double master program, between applied physics and mathematics. I hope you're not enrolled in any such things. And by that time, it was just a starting problem. And I talked to the student, it was for the examination, and I understood that he has no idea about linear relations. So the fact that this relation gives you a line at the plot was somehow new to him. I hope that it's not new to you. Otherwise, I would need to explain this in more detail and perhaps make a couple of lines like this. But at least in the Netherlands, people kind of trained at school to make such linear plots. Right. Doesn't it give a suffice? It gives you a half plane, right? I draw only lines when this expression becomes zero. Then, if I want to understand where this relation is fulfilled, usually I draw it as follows. Let me just redraw this different color. I draw a line. It has 2 sides, and I need to kind of denote where this actually holds, where it's bigger than 1. And usually I just put dashes on one side of the line, which means that everything, whether the side with dashes in all points, this equation is satisfied. Good. Then I put yet another line, and dashes are here. Fine. So I have already different region where two conditions are satisfied. All right, yet another line. Dashes are here. it's good that for parallel lines, dashes are at opposite sides. Good. This condition is, these three conditions are satisfied in this region. And finally, the fourth line. Again, I put dashes. In this way, we kind of cut the diamond from the whole plane with 4 cuts. Does it explain the situation? Fine. Then let us talk about master equation. Right. One can go pretty complex with even with simple master equations. That's why it is intentionally kept simple. So we tune all these voltages in such a way that there are only 2 states available: state 0 and state 1. And then there are only 2 possible rates. All electrons are supposed to go from, let's see, where does it go? From right to the left. Okay, it goes from right to the left. What does it mean? It means that this comes from the right junction. It comes from the right. And there's another rate in opposite direction, which is to the left. So electron which is present, electron present in the element jumps to the left. Fine. These diagrams are very useful when you discuss master equation, when you try to make up a master equation. It is somehow recommended. Good. Then the master equation itself, it's a probability balance. So we see that change of probability to be here has 2 contributions: outgoing terms. This outgoing rate and okay, probability. The system has to be in state 0. That's why here we find probability at 0. Also could be income rate. In this case, the system has to be in the state 1. We have P1. We look at stationary case. These probabilities are 0. So we find this 2. For 2 states, 2 rates, it's kind of very simple equations. Okay, let me go on. The rates are expressed through conductances, and what one finds here is basically a corresponding energy difference. And right, that can be. Now one has to, for instance, concentrate on the right junction or left junction. Doesn't matter because the currents are the same. Take the probability we have calculated, multiply it on with the rate. Okay, here we are. Okay, if we have a diamond and suppose we go at this line, these rates are proportional to energy differences, and as we discussed, these lines are where these energy differences are zero. So each rate actually goes to zero at each boundary. Yeah. Which means the current also goes to zero at each boundary. And if we plot now current along this line, yeah, has to be zero here and here. So the dependence is somehow like this. Good. So it was a simple extension of the lecture about Coulomb blockade. Let us see what can we do now. More a little bit more complex exercise in this direction. To demonstrate that it can easily go more complex if you just increase the number of elements a little bit. Okay, it's a solution. I've got to go to the problem. Yeah, here it is, double set. So now we have two islands and electrons have to jump through both islands. First of all, first thing by investigating Coulomb blockade systems is to understand the charging energy. The system was chosen in such a way that, yeah, that's the formula is simple. What are elements in this formula? Of course, it depends on number of charges in each island. There are capacitances involved, and there are gate voltages involved. What is actually missed here? Somehow it's been assumed that all gate capacitances are much smaller than capacitances of this tunnel junctions. Okay, with this there is a relatively simple formula for charging energies. Good. Then again, the formulation of the exercise is to make your life simpler. So it's been assumed that the gate voltages and the bias voltages are in the window where only two, four configurations are allowed, corresponding to different numbers of N1 and N2. To understand what are eventual conditions on V gate 1, V gate 2, one has to do some work, which is in principle simple work, but rather tedious. One has to write all energies and understand what would be the region where energies are such that no transition from this subspace is allowed. There is a question. Why is it so? This is to confuse you first. Second, it relies on this property of the system. So it has been computed for certain ratio between capacitances involved, and right, this capacitance is a half of these two capacitances. So this energy has been specified to a certain value of capacitance. Fine. Now let us see what do we do. Let us understand the task first. Again, it's more about master equation than about Coulomb blockade. So one has to write down master equation, and it's a kind of useful ability to train yourself. Solve this equation, which means give expression for probability in terms of the rate. After that, having this formula, one can compute the rates, which are given by energy differences, and compute the rates, and finally get the current. Okay, step by step. Let us see, let us switch to the solution. Let us here it is. Let me make it comprehensive also. I kind of that's also useful for my orientation. We have 4 states. This point is clear because N1 and N2 can go between 0 and 1. Okay, let me put these states. Just draw it. And now I want to figure out which rates work if electrons go where they're supposed to go. From the left to the right. Okay, in this case, they go from the left to the right, so left electron is increased. And let me just indicate that it happens as a transfer through junction 1. What happens further if we have this state? We can go here. That involves transitions through the junction. Let's see, let's say junction. Okay, 1, 2. And then another electron can come to the left, and we go to 1, 1. So what do we do if we come to 1, 1? All right. It can go here. And in this case, second junction is involved. Something else? You can help me to finish this diagram. I would also have a difficulty, but what warns me that the figure is somehow not very symmetric. So there has to be some extra line just by symmetry consideration. And look, what can happen, the electron from the right can, in the right island, can go faster to the right. And then it becomes state yes, we get it. Right, good. So when we draw this picture, we are ready to write down the equations. It is pretty much automated. For instance, this equation, there is a plus coming from state 0, 1, minus when it goes to state 1, 0. For this state, right, there are 2 incoming rates here and here, 1 outgoing rate. Good. That's why it's always useful, also during examination to start with drawing such diagram. Understand which rates are allowed. When you draw a diagram, writing an equation is already no problem. Right. So we want to move on. Yeah. Then there are possible, well, after that one understands which energy differences are relevant and express them. And okay, those are relevant rates. We didn't put bias voltages, assuming that it's not important. And right now we need to solve this equation. Good. It's again a stationary case linear equation on probabilities. It is since there are 4 probabilities are involved, the solution looks a bit more complex than for 2. Anyway, it can be solved, and this is final expression for the current. Something like this you might be asked during the examination. It's kind of more or less same complexity level. Also kind of amount of hints and simplifications. It's about the same as during the actual exam. So please don't be confused by strange approximations, assumptions. They are all to make your life easier rather than to confuse you. Fine. I guess I've done this. Let me stop the video, and I will be here to answer your questions.